Hey everyone, my name is Arifa and I'm a PhD student at the University of Wisconsin-Madison. And today I would like to talk about a project that I'm working on, which is modeling neutrino emission from active galactic nuclei as identified by IceCube. So as you have heard a million times, what is IceCube? IceCube is a neutrino detector that is embedded in the ice of the South Pole, and it contains photomultiplier tubes that detects Cherenkov radiation when an incoming neutrino beam interacts with the ice of the nucleus of the ice. So over the years, IceCube has detected a diffuse flux of astrophysical neutrinos, and lately it has started to pinpoint locations of both extended and point sources that make up these diffuse neutrinos. So the two most significant point sources that IceCube has seen are NGC 1068 and TXS 0506, both of which are AGNs of about 10 to the 7 solar masses, and they are located in the northern skies. So NGC is a Seyfert 2 galaxy that is located quite close to us at a redshift of about 0.004, and it has been a steady source in that between 2011 and 2020, in this 10-year window, IceCube has seen about 79 neutrinos. But on the other hand, TXS is a high energy blazar that is located much further from us at a redshift of about 0.34. It's a transient source. And so between 2014 and 2015, IceCube has seen 13 neutrinos. And in September of 2017, we have detected 290 TeV neutrinos. So what exactly are these AGNs? AGNs, or active galactic nuclei, contain supermassive black holes at the center of their active galaxies. They contain sites that can accelerate protons, which I will elaborate more later on. And they also are able to produce neutrinos in the dense targets that are around them. So they act as both an accelerator and a target. So it contains a high optical depth due to matter falling and accreting around the black hole, as well as a high density of X-ray radiation being given off at the accretion disk, and as well as the corona that is around this supermassive black hole. So the goal in this project is to use astronomical data regarding this AGN and make predictions about neutrino flux and gamma ray flux and make comparisons to data. So how are protons accelerated? There are about 3 mechanisms. The first one is shock acceleration. So there are multiple shock waves that are surrounding the supermassive black hole, and they act as magnetic mirrors. And so when there's an incoming proton beam, they are repeatedly reflected between the shock wave fronts and thereby accelerating them in this process. The second method is via magnetic reconnection. So there's a high density of magnetic fields surrounding the supermassive black hole. And sometimes these magnetic fields break and reconnect with one another to form a more aligned configuration. And in this process, a lot of magnetic energy that is stored in these lines, few lines are released and passed on to any protons that are around them, thereby accelerating them in the process. And the last method of acceleration is when the incoming proton beam collides with magnetized plasma blobs, and energy is being absorbed into the proton and they get accelerated. So an accelerated proton beam can produce neutrinos by 2 channels. One is the PP interaction and one is the P gamma interaction. So when an incoming proton beam meets another proton target, such as matter that is around the black hole, it can form pions, all 3 types of pions in equal amounts. And also if it encounters like a photon, like an X-ray photon that is existing around the supermassive black hole, it forms a positively charged pion and a neutral pion. So neutral pions go on to decay into gamma rays, as shown by the yellow boxes, while charged pions form electron and muon neutrinos and antineutrinos, as shown by the blue boxes. So now I would like to talk about the steps on how neutrinos are produced in AGN. So we model the rate at which protons are injected and accelerated in the accelerator parts of the AGN as a single power law, where gamma P is the spectral index and QP0 is the normalization constant, that depends on the value of the pivot energy, which is EP naught. And we have also taken the energy of the proton to be much higher than its own rest mass energy. Next, when the proton encounters a target, it produces neutrinos using these two channels, which depends on what kind of target that they encounter. And the derivation of the PP and the P gamma channel is actually given at the bottom. And when the neutrinos are produced, gamma rays are also produced along with them. And so one point that I want to highlight is that these are the attenuated production rate. And because they depend on this parameter called the optical depth, as denoted by tau. So optical depth basically is a measure of how much an incoming signal is able to be transmitted through a medium over a certain distance. So as the neutrinos leave the detector and propagate towards us, they can encounter opaque medium either at the source or in the extragalactic background light on their way to us. But the thing is, they do not get absorbed. They survive entirely, unlike the gamma rays that are produced with them. The neutrinos are then detected by IceCube, whereas the gamma rays, any surviving gamma rays, are picked up by the Fermi-led telescope. So the neutrino flux that IceCube sees is given by equation 3 over here. And we see that they have picked up redshift dependent terms such as the luminosity distance and a factor of 1 plus z due to the redshifting of the neutrino energy itself. So in this part of the talk, I would like to derive the optical depth of the target. Not derive, but give dimensional analysis arguments. So for the P gamma interaction, we adopt a corona disk model. So tau P gamma depends on this parameter called the X-ray column density. And the X-ray column density is derived from the X-ray luminosity and the X-ray energy observed of a particular black hole. And if neutrinos are to be produced in NGC 1068 by the P gamma interaction, we have calculated that they have to originate from within 10 Schwarzschild radii of the black hole, which is pretty close to the black hole itself. So the next method is the PP model, and we adopt the infall shockwave model. And one important quantity is the proton column density, which is NH. And the proton column density basically encodes how much matter is being accreted around the black hole. And another important parameter is the free fall velocity with respect to the speed of light, which is the last term in the bracket. And that is a critical property of the shock waves, given that shock waves develop within the matter that is accreting around the black hole. So for NGC 1068, using these dimensional analysis arguments and input data from astronomy, we have calculated the optical depth to be 0.8 in the PP case and 0.1 in the P gamma case. And now that we have calculated these values, we have kind of plot the neutrino fluxes. So the neutrino fluxes are in the solid lines, and the accompanying gamma rays produced are in the dashed lines. And we have plotted for both PP case, which is in the red, the red lines, and the P gamma case, which is in the brown line. So what we did was we assume a neutrino flux based on the PP interaction case. And this is consistent with the IceCube data at 95% confidence level. And using this, we then make a prediction on what the neutrino flux would be if it were to be produced by the P gamma channel. And for the corresponding neutrino fluxes, we make a prediction on what the gamma ray fluxes would be. And note that these gamma ray fluxes produced are around about the same energy range as the neutrino fluxes themselves. And this is because they are uncascaded and unattenuated. But what observations show is that the neutrinos, the gamma rays seen by Fermi is at a much lower energy at GeV to TeV range. And this is because they get cascaded along the way and also attenuated. So the next part of the project going forward would be to reconcile and understand how our predictions of this model with these astronomical data. So to understand the cascade process, one way of looking at it is through the Heitler model, in which a gamma ray could lose energy by pair production or Bremsstrahlung radiation, and it produces many layers of charged particles, and which is denoted by N. And these development of layers stop when the gamma rays reach the pair production threshold energy. And the last layer of energy are the last generation of particles, which is what we detect using our detectors. So in summary, we have seen that neutrino production rate depends on the optical depth of the target, and that gamma rays are observed at energy much lower than the neutrinos themselves. And so the idea would be to understand why a bit more about why this is so, and to calculate the cascaded and attenuated gamma ray flux, and to compare it to data. And the next step would be then to extend this model to jet-like sources like TXS and understand how the jets would contribute to this model. Thank you.
Thank you, Arifa. Do we have questions? Oh, you have to sit in the front.
Yeah, thanks. I was wondering, so for the gamma attenuation, you seem to consider only the way, like the propagation attenuation, right? Because the Heitler model in principle is only valid for propagation.
Yeah.
You don't consider any attenuation close to the source or in the source?
We do consider attenuation close to the source, so there can be cascades in the source.
But how?
Because if a gamma-gamma interaction.
No, so but with the same model.
We have to extend the model, so that's future work.
Okay, yeah. Because I would be a bit careful maybe, because this Heitler model, depending on how the source parameters are, cannot be, sometimes it's not super precise.
It's not super precise.
Because it doesn't consider feedback mechanisms between the gamma rays.
I see.
Yes, I mean it's a cascade model, so naturally it's not something that would consider the feedback mechanisms that you can have in source.
Meaning it just goes in like one direction.
Meaning the gamma rays, the secondary cascaded gamma rays, they don't have an impact on your primaries again.
Mm-hmm.
And in that sense, it's very good for propagation, but yeah.
Okay. This was a question.
Thanks for the really nice talk. I have a very naive question on slide 11, where you're showing your expected neutrino fluxes. Yeah, so in the equation number 3, I see that the flux is proportional to 1 plus the redshift. So, we also have a factor outside. So if I understand this correctly, it just means you have a larger area of the universe to cover at larger redshifts. So you expect a greater flux. That's it.
Yeah.
Okay.
Exactly.
Okay. Thanks.
That's basically 1 over the co-moving volume squared.
Right.
Yeah. Actually, I had a question on the neutrino flux prediction. So for the P gamma case, you assume that the opacity stays constant in energy, so there's no modulation from the photon spectrum. So this is basically some upper limit, the most optimistic case that you consider. Okay.
And we also assume that most of the interactions, like as we can see from this data, like we assume that P gamma will happen much lower than PP, because it is not as optically depth as it would be to a PP interaction. Mm-hmm. So we assume that most of the neutrinos could be produced by just PP.
PP interaction. Yeah. Mm-hmm. Okay. Other questions? Yeah, maybe one last question.
So here on this slide, you calculate the optical depth of the target by dimensional analysis, you said. So I wonder, how do you know that there is no numerical factor which is dimensionless, which you don't know about?
I think there could be, but the way we use it is dimensional analysis is that it's quite loose, and even if there's a prefactor, it would be something like 3/4 or something that comes from area integration, but it won't be something like many orders of magnitude. Yeah.
Okay, let's thank Arifa again